Section 7.7, Improper Integrals. Up until now, we have always considered integrals of the form integral from a to b of f of x dx, where f was always continuous on the interval from a to b, and so f was always bounded on the interval from a to b. Also, our interval of integration, ab, has always been a bounded interval, meaning neither a nor b could go to positive or negative infinity. So the question before us today is, what if the interval itself is unbounded? So suppose we were to look at an integral of the form from a to infinity of f of x dx. Or, what if f, the function itself, f, was unbounded on the interval from a to b? Say f went to either positive infinity or negative infinity at one of the endpoints. If either one or two happens, then the integral is called an improper integral. It turns out that if the interval is unbounded, we call this an improper integral of the first kind, and if the function itself is unbounded on a bounded interval, then we call this an improper integral of the second kind. It turns out that these two categories or classifications of improper integrals will guide our thinking throughout this section. So let's look at improper integrals of the first kind. So the setting here is suppose that f is a continuous function on the interval from a to infinity. Then we want to know how to handle this improper integral, the integral from a to infinity of f of x dx. We will do so by defining this improper integral as the limit as r goes to infinity of the integral from a to r of f of x dx. In other words, to handle this improper integral, we're simply going to consider this proper integral, compute this proper integral, and then take the limit as r goes to infinity. If that limit exists, then we say the improper integral converges, and its value is the value of that limit. If not, then we say that the improper integral diverges. So the idea is to replace an improper integral with a proper integral, compute the proper integral, and then take the limit. Geometrically, the situation is, if we want to know all of the area that's under this curve from a on to infinity, then we will take this problem and turn it into something that's familiar with us by calculating the area from a to r, which is a proper integral and done with Calculus 1 techniques. We'll calculate this integral as a function of r, and then we'll take the limit as r goes to infinity. Let's look at an example. So for example 1, we have the integral from 1 to infinity of e to the minus x dx. This is an improper integral of the first kind because the interval is infinite. We will rewrite this as the limit as r goes to infinity of the integral from 1 to r of e to the minus x dx. This is a proper integral. We know how to anti-differentiate this and evaluate between limits. So now we need to take the limit of this expression as r goes to infinity. Now as r goes to infinity, this is a decaying exponential, so this term goes to 0. This is just a constant, so it's not affected by the limit as r goes to infinity. We simply get 0 plus e to the minus 1, which comes out to be e to the minus 1. Geometrically, this says if we were to graph the function f of x equals e to the minus x, we were to look at the area under the curve from 1 to infinity, that this region would have an area that we call e to the minus 1. It's a finite amount of area, and that amount is e to the minus 1. We would say the improper integral converges to the value of e to the minus 1. As a second example, take a look at the integral from 1 to infinity of e to the minus x dx. Again, this is an improper integral of the second kind, so we rewrite this as the limit as r goes to infinity of the integral from 1 to r of 1 over x dx. This is an antiderivative we're familiar with. We anti-differentiate, we evaluate between limits, we take this expression as a function of r, we take the limit of this as r goes to infinity. Recall that the natural log of 1 is 0. The natural log function as r goes to infinity, the ln of r goes to infinity, so this term goes to infinity. So that says that this limit goes to infinity, and here we say that the improper integral diverges because this was not a finite number. Geometrically, this says if we were to graph the function 1 over x and to consider the area under the curve from 1 on to infinity, that this region would have an infinite amount of area because the improper integral diverged. As a third example, just so we look at one where we're not always integrating out to infinity, you can also integrate to minus infinity. Suppose we took the integral from minus infinity to 2 of 1 over 1 plus x squared dx. Geometrically, the graph of 1 over 1 plus x squared looks like this. Here we'd be finding the area under the curve from minus infinity to 2. And so we want to know if this is a finite amount of area or an infinite amount of area. So we'll rewrite this integral, this improper integral, as a proper integral. Since here, this is the endpoint that is going off to minus infinity, we will rewrite this as the integral from r to 2 and take the limit as r goes to minus infinity. This is an antiderivative we should be familiar with from Calculus 1. The antiderivative here is tan inverse of x. We evaluate between limits. We get this expression in r. Now we need to take the limit as r goes to minus infinity. This is just a number, so we leave it alone. Here you may recall what the graph of the tan inverse function looks like, or the arctan function looks like, and you can look it up if you need to. But as r goes to minus infinity, tan inverse of r goes to minus pi over 2. So we get tan inverse of minus a minus pi over 2, tan inverse of 2 plus pi over 2. This improper integral then converges, and this is its value. And that would say that the area under the curve here that we have shaded has the numerical value of tan inverse of 2 plus pi over 2. So note in these examples that e to the minus x in our first example, that function goes to 0 as x goes to infinity, and the improper integral from 1 to infinity of e to the minus x dx converged, while on the other hand 1 over x also goes to 0 as x goes to infinity. This was in our second example, but its improper integral from 1 to infinity of 1 over x dx diverges. So this is a very important point to make here and for you to understand. Just because a function goes to 0 as x goes to infinity, that is not enough to guarantee convergence of the improper integral. This is a very commonly misunderstood point here. So it seems that the convergence or divergence of an improper integral of the first kind not just depends on whether f goes to 0, but how fast f goes to 0 as x goes to infinity. So the question is, how fast is fast enough for a function to go to 0 in order for its improper integral of the first kind to converge? We'll explore this answer in the context of what are called p integrals. So let's define that. Let p be a given power. We call the integral from 1 to infinity of 1 over x to the p dx, we call this integral a p integral of the first kind. P integral because the integrand looks like 1 over x to a p power, and first kind because it's an improper integral of the first kind. So the question here is, for what values of p will this improper integral converge or diverge? Well, in our previous example, we already answered this when p had the value of 1. We saw that that integral diverged. So suppose that p is not equal to 1, and let's compute this integral generally for an arbitrary p that's not equal to 1. Okay, so we rewrite this improper integral of the first kind as a limit of proper integrals. This is a straightforward power rule integration, so we apply the power rule, we evaluate between limits, and now we want to take the limit of this as r goes to infinity. So notice this is independent of r, so it's not affected by the limit. We really need to concentrate our analysis right here. Now it's very important to realize that as r goes to infinity, that whether this limit exists as a finite number or not depends on whether this term or this part of this first term is finite or not. Notice that since r is getting big and positive, r to the minus p plus 1 goes to 0, and so this will be a finite number if its exponent is negative. On the other hand, if its exponent is positive, then this quantity will grow without bound. It will go to infinity. So if we want this improper integral to converge, then the math here demands that this exponent here be a negative number. So if we proceed with the stipulation that minus p plus 1 is less than 0, in other words, p is greater than 1, then we'll take this limit. This term will go to 0. This term is going to a 1 over minus p plus 1. And after we distribute the minus, we get that this value, the value of this limit is 1 over p minus 1, provided the original exponent here was negative, which is equivalent to saying p is greater than 1. And on the other hand, if p is less than or equal to 1, we saw that this integral would diverge. So let's summarize our results here. For p integrals of the first kind, they converge if the power p is greater than 1, and when they do converge, they converge to the value of 1 over p minus 1, and they diverge if p is less than or equal to 1. It's very important to remember that p equals 1 is the critical exponent here that separates convergence of this improper integral from divergence of this improper integral. Exactly when p is 1, you get divergence, and if p is greater than 1, you get convergence, and if p is less than 1, you get divergence. Next, let's turn our attention to improper integrals of the second kind. So here, we want to suppose that f is continuous on the interval from a to b, not including b. And let's just say that f tends to either plus infinity or minus infinity as x approaches b from the right. I'm going to do this analysis where the function becomes unbounded at the right endpoint, but it would be exactly the same idea if we are having f become unbounded at the left endpoint or somewhere in between. Then, if we look at this integral from a to b of f of x dx, this is an improper integral because our function is becoming unbounded at an endpoint. And so we define this as the limit as r goes to b from the left of the integral from a to r of f of x dx. You need to be very careful when you approach an integral like this because it's not as immediately obvious that it's an improper integral as when we were looking at improper integrals of the first kind. We could easily see that the integration was either going to infinity or minus infinity, and so we could spot that it was an improper integral. Now you have to be on your guard every time that you have an integral like this of whether it could be an improper integral of the second kind. You always need to check whether your function becomes unbounded on the interval. And if so, it's an improper integral of the second kind, and you'll proceed as in these examples. The geometry of the situation here is you could imagine, say, a function that has a vertical asymptote at x equals b, and we're integrating from a to b, so we are integrating up against the vertical asymptote, so to speak. The question is this a finite amount of area or an infinite amount of area? And the way we handle this problem that we've not encountered before is simply by backing off of the asymptote a little bit, integrating f from a to r. This would be a proper integral. F is continuous here. F is not unbounded here. And then when we compute this expression as a function of r, then we take the limit as r goes to b from the left. Let's look at some concrete examples. So here, if we have the integral from 1 to 2 of 1 over x minus 2 dx, notice this function has a vertical asymptote at x equals 2, so it's an improper integral of the second kind, and it occurs at our right endpoint. So we will rewrite this as the limit of this proper integral, the limit as r goes to 2 from the left, of the integral from 1 to r of 1 over x minus 2 dx. This is an integral that we're familiar with, so we'll anti-differentiate, we'll evaluate between limits, and then we need to simply take the limit as r goes to 2 from the left. Here we just get the ln of the absolute value of minus 1, which is the ln of 1, which is 0. Here, if you think about what the natural log function does, as r goes to 2 from the left, the argument of the natural log function is going to 0, so the natural log function is going to minus infinity. So overall, this limit is a minus infinity, and since it is not a finite number, we say that the integral diverges. Geometrically, that says if we were to graph the function 1 over x minus 2, we were to integrate from 1 to 2, that this would be an infinite amount of area. We would say that this improper integral diverges. Example 5. Let's look at the integral from 0 to 1 of 1 over x dx. Notice this is very similar to one of our examples earlier, except there we were integrating from 1 to infinity, and here we're integrating from 0 to 1, and that makes an important difference. Of course, this function has a vertical asymptote at x equals 0. This is an improper integral of the second kind. So once again, we will rewrite this as a limit of proper integrals. We'll anti-differentiate, evaluate between limits. Now we'll take the limit. As r goes to 0 from the right, this is going to minus infinity. This is just a 0. So again, the minus infinity gives us a plus infinity, and we get that this improper integral diverges. Let's look at one more. If we look at the integral from 0 to 1 of 1 over the square root of x dx, yet again we have a vertical asymptote at 0 at our lower endpoint of integration. So we write this as the limit of proper integrals. We anti-differentiate using the power rule. We evaluate between limits. Then we take the limit as r goes to 0 from the right. Here we just get 2. Here we get 0. And so the limit here is 2. This integral converges. Notice it's very important here that you calculate the proper integral and then take the limit. A very common mistake that students make is they mix up the order of taking the limit and computing the integral. You need to compute the proper integral first, then take the limit of that expression to get the ultimate answer to your improper integral. Okay, next let's look at p integrals of the second kind. So let p be a given power. We call the integral from 0 to 1 of 1 over x to the p dx a p integral of the second kind. P integral because the integrand looks like 1 over x to the p power, just like last time, and it's second kind since this is an improper integral of the second kind. So for what values of p will the integral from 0 to 1 of 1 over x to the p dx converge or diverge? Well, we already saw by direct calculation in example 5 that when p is equal to 1, the integral diverges. So let's calculate this p integral of the second kind in general when p is not equal to 1. So we will rewrite this as the limit as r goes to 0 from the right of the integral from r to 1 of x to the minus p dx. We'll anti-differentiate this using the power rule. We will evaluate between limits, and when we evaluate between limits, we get this expression in r. So here's where we have to concentrate on our analysis because we need to see when this limit is finite versus infinite. When it's infinite, the improper integral diverges. When it's finite, the improper integral converges. Now this time r is going to 0 from the right, and last time r was going to infinity, so that's going to change our analysis. So if you focus on the r to the minus p plus 1 part, since r is going to 0, r to the minus p plus 1 will only stay bounded if the exponent is positive. And so if the exponent is positive, then p would have to be less than 1. Because if the exponent were negative, then we would have an r in the denominator that is going to 0 and the quotient would blow up. So if we make the stipulation that the exponent on the r is positive, in other words, that p is less than 1, then this term will go to 0. This term just is what it is, which is 1 over 1 minus p, provided that p is less than 1. And so this improper integral of the second kind, this p integral of the second kind, converges provided p is less than 1, and it diverges if p is greater than or equal to 1. And we summarize that here. The p integral of the second kind converges when p is less than 1, and when it converges to the value of 1 over 1 minus p, and it diverges if p is greater than or equal to 1. Pay attention that this is exactly the opposite of what happened with p integrals of the first kind. Remember, they converged when p was greater than 1 and diverged when p was less than or equal to 1. So here they swap roles, and you need to keep that in mind. Note that yet again, p equals 1 is the critical exponent here that is separating convergence from divergence. Now sometimes we will need to determine convergence or divergence of an improper integral when we cannot explicitly compute the integral. So I'll just use this theorem from the textbook. This is called the comparison test for improper integrals. So assume that f and g are continuous. F's greater than or equal to g, which is greater than or equal to 0, so your functions have to be non-negative on your interval of integration. And the theorem says that if the improper integral, the integral from a to infinity of f of x dx converges, then the improper integral from a to infinity of g of x dx also converges. And if the integral from a to infinity of g of x diverges, then the integral from a to infinity of f of x also diverges. So if you think about it like this, if everything here is positive, or at least non-negative, if f is bigger than g and f converges, then it forces g to converge, because how could g's integral diverge to infinity if it's below something that converges? And on the flip side of that, if g diverges, or if the integral of g diverges, I should say, and the integral of f is even larger, then it must diverge also, assuming everything is non-negative. So let's look at how this is used in practice. So here, example 7, use a comparison, not a direct calculation, but a comparison to determine if the integral from 1 to infinity of e to the minus x over x dx converges or diverges. Now I picked this example on purpose because you cannot directly calculate this integral. It's beyond the reach of any of the methods that we have right now. So let's see if we can finesse this using the comparison theorem. Well, first off, we notice that x is greater than or equal to 1. So if x is greater than or equal to 1, that says that 1 over x is trapped between 0 and 1. So now, since e to the minus x is positive, then we can multiply all three parts of this by the positive quantity e to the minus x. Here we get a 0. Here we get an e to the minus x over x. Here we get an e to the minus x. And now we have things set up according to our comparison theorem. We have everything here is positive. We have that this is our f and this is our g. And now the question is, do we have some kind of relationship between these integrals? Well, the relationship between the functions is that everything here is positive and this function is less than or equal to this function. Therefore, the integral of this function from 1 to infinity is less than or equal to the integral of this function from 1 to infinity. But we know something about this integral. In fact, this was the very first example in this section that we worked. We calculated this and we showed that this integral converges. Since this integral converges and it's greater than this integral, it forces this integral to converge as well by the comparison test. Let's look at another example. So we'll use a comparison to determine if the integral from 1 to infinity of dx over the square root of x cubed plus 1 converges or diverges. So I'm trying to pick examples that have some different looking integrands so you get some practice and some looks at making different inequality arguments. So let's try not to be too overly fancy here. Let's use something that's pretty straightforward. So we'll just notice that if we compare the square root of x cubed and the square root of x cubed plus 1, this must be larger because notice we've added 1 inside the square root here. So if this is greater than this, and everything here is positive, then when we reciprocate, that if this is larger than this, then the reciprocal of this must be smaller than the reciprocal of this, and everything here is positive. Now we're setting up things like in our comparison test. If everything here is positive and this g is less than or equal to this f, then the integral of this g is less than or equal to the integral of this f. This is an integral we're familiar with. We could just rewrite this as a p integral of the first kind with a p equals 3/2, which is greater than 1. Therefore, this integral converges. And this integral is less than or equal to this integral, and everything's positive. So this integral must also converge by the comparison test. Let's show you that these ideas can also be used when you have an improper integral of the second kind. So let's use a comparison to determine if the integral from 0 to 1 of e to the x over x squared dx converges or diverges. Well, let's begin with something very basic. Let's notice that e to the x, if you just think about what the graph looks like, e to the x is greater than or equal to 1 for all x that are positive, but in particular between x's that are between 0 and 1. If that's true, then we can multiply both sides of this by the divide both sides of this by the positive quantity x squared. And if we do, everything here is positive, and it is ordered with this f being greater than or equal to this g, which is greater than 0. So if this function is greater than or equal to this function and everything is positive, then the integral of this function is greater than or equal to the integral of this function. But this is a function that we're familiar with. This is a p integral of the second kind with a p equals 2. 2 is greater than 1, and so this integral diverges. So that says that the integral that we're interested in is greater than or equal to a known integral that diverges. By the direct comparison, that says that this integral must diverge also. Okay, so in this section we looked at the definition of an improper integral, both of the first kind and of the second kind. We've computed some of these directly. We've also looked at p integrals of the first kind and p integrals of the second kind. We're going to see that they play a significant role going forward in the course when we want to compute various things. And then we've also seen that in the situations where we can't directly compute an improper integral, sometimes we only want to know convergence or divergence, that one of the tools we have is to do a comparison test.